This is a very traditional and frequent type of problem here where we have a reservoir of some kind, in this case a tank of water, and we have a rate that something is coming into it, the water is coming in, and a rate that the water is going out. What mixes this problem up a little bit is the fact that the rate that the water flows in is given as a continuous function that we have an explicit formula for, whereas the rate going out, we're told that the function is differentiable and decreasing, but we only have selected values of the function. So anything we're going to do with that second function, the rate of outward flow, is going to have to be an approximation of some sort. Finally, we're given an initial condition. The volume of water in the tank at time 0 is 50,000 liters. What I've done is I've added the concepts on the right-hand side that we're going to be making reference to throughout this problem. And I've also drawn a diagram that I think is going to be helpful just in picturing what's going on. Namely, we have that volume of water as a function of time, but we've got the flow rate in W, the flow rate out R. What that means, and I think this is also valuable, is that the volume as a function of time, its rate of change, V prime, is defined to be W minus R. All right, well, let's jump into the first question. We have to estimate R prime of 2. Estimate suggests that perhaps we can't know an exact value, and that should be reassuring because, as you see, we don't even know what R of 2 is, and R prime is something we can only infer by comparing the different R values at different times. So in this case, there's no reason that we need to do anything fancier than what we would simply do in a regular Algebra 1 problem. Namely, we just say, well, the value at 2 is just as well estimated as the average rate of change over a time interval that surrounds time 2. That's about as good as we can get. And so we're just going to use this Algebra 1 formula that we're all familiar with, namely the average rate of change is just y2 minus y1 over x2 minus x1. In this case, we're going to write that like this. So we estimate R prime of 2 as the average rate of change on the interval for which we have data that's closest to R of 2. And so I'm just going to say from t equals 1 to t equals 3. Okay? So that just means R of 3 minus R of 1 over 3 minus 1. And when we put the numbers in, what do we get? 950 minus 1190 over 2, and that comes out to negative 120 liters per hour squared. Now, why do I know it's hours squared? It's because R itself is a rate of change, liters per hour. They're asking about R prime. That's the rate of change of R. And so that means per hour again. That's why we use that hour squared notation. Okay. What do we have in B? We're going to use a left Riemann sum. We're going to work with the data in the table to estimate the amount of water removed from the tank. Okay. Well, left Riemann sum because what we're doing is we have a rate, R prime of t. If we integrate it from 0 to 8, if we find the signed area under the R prime of t curve, we will have found the net change in R. Or, I'm sorry, the net change of total amount of water removed. And so we're going to say that water removed is an integral from 0 to 8 of r of t dt, which we estimate as, okay, now here I've got this left Riemann sum. Remember, the only thing that you have to keep in mind is that we're just adding up areas of rectangles, but for each rectangle we're using the leftmost height of the function. And so for this interval from 0 to 1, we're going to use this value, 1340. For the interval here, we'll use this value. For the interval here, we'll use this value. For the interval here, we'll use this value. And notice we don't even make use of this value. That's just the nature of a left Riemann sum. So let's write it out. It's 1340 times, what's the distance between 0 to 1? Right, 1 minus 0. Plus 1190. What are we going to multiply that by? 3 minus 1. Plus 950. Notice that interval is particularly long in time. It's 3 hours, 6 minus 3. Plus 790. And what's that interval? 8 minus 6. Put it all together, I think you get 8050, which ordinarily I wouldn't even write out on the form. Remember that you're not required to simplify, but I happen to know that in this particular case they're going to ask for that number later on. And so in fact I did the calculation on the calculator and I stored the value in A. I'm just going to define this as A. Now, is it an overestimate or an underestimate? Well, here notice that I've drawn the left Riemann sum for a decreasing function. And since for each interval that we're considering, we're always working with the left height, given that the function is continuously decreasing, the left height is always going to be an overestimate for the signed area. These parts that I'm coloring in are telling us how much we're overestimating by. So I'm just going to say because r is decreasing over the interval, a left Riemann sum is an overestimate. Okay. Now in part C, we're trying to estimate the total amount of water that's left in the tank at the end of 8 hours. If you think about it, they've already told us how much water is in the tank at t equals 0, and so that should raise in your mind the notion that we can apply the fundamental theorem of calculus to calculate how much that has changed. Namely, in this case, we'll be saying the water at 8 hours equals how much water there was at 0 hours plus the integral of the rate of change of the water from 0 to 8. So let's write that out. We have the volume at 8 equals the volume at 0 plus the integral from 0 to 8 of v prime of t dt, where we recall that v prime is made up of w minus r. So let's just write that again. We're going to split this into two separate integrals. Okay? This will be the integral from 0 to 8 of w of t dt minus the integral from 0 to 8 of r of t dt. See how that one integral turns into two? So what are our values? Let's plug things in. First, we know that v of 0 is 50,000. Second, we know that we've estimated r of t to be 8050. So what remains is this wt dt from 0 to 8. That's what we have to calculate. And to do that, we'll use the calculator. So what you can see is I've already put in the formula for w of t, 2000e to the negative x squared over 20. Put that in as y1. And again, I remind you that you want to put the formula in just once and then reference it as y1. So now we can go to the main screen, and what you'll see I've done here is I did math 9 from 0 to 8 of y1 with respect to x, simply because even though the problem is couched in terms of time, we're always working in the calculator in terms of x, unless we're in parametric mode, and that's a rarity. At any rate, that integral of w of t from 0 to 8 gives us 7836, and I can put the other numbers in now, 50,000 minus 850, plus this value that we just got, approximately 7836, yields a final answer of 49,786. So let's just pencil that in now. This, we said, came out to 7836. And so our final answer, put all those numbers together, gives us 49,786. And we'll say approximately. And the units are liters. I would add numbers after the decimal place, except that the problem specifically asks me to approximate to the nearest liter. Okay, part D. In part D, for many students, is knowing what it is we're supposed to work with. The key lies in the language of the question, namely, is there a time when w of t equals r of t? Notice that they don't ask you to find the time. And that's so characteristic of the various theorems that we learn in calculus, the intermediate value theorem, the mean value theorem for derivatives, and the more general mean value theorem for functions. Not where the point is, but whether such a point exists. In this case, we're going to be using the intermediate value theorem. Now, again, it's something that you need to be familiar with, but when they ask whether w of t equals r of t, for some t is the same as is there a t such that w of t minus r of t equals 0. Why do we know that the intermediate value theorem applies? Well, w of t minus r of t is continuous by inspection for w of t. And because differentiability implies continuity for r of t. Okay, so we know the intermediate value theorem applies. Therefore, IVT applies. So we need to find whether there is a 0 point. All we have to do is find a point where w of t minus r of t is greater than 0, find another point where it's less than 0, and then we know that some intermediate value in time must have a place where the difference of rates is exactly 0. So we have w of 0 minus r of 0, we're given that. That's going to be 2000 minus 1340. We know both of those numbers. That's clearly greater than 0. But we also have W of 8 minus R of 8. And we know that's going to be, what do we have? I calculated it in the calculator. Another good reason for putting in the formula only once, because I can find y1 of 8. It's about 81. And I think our R of 8 value up from the table, up here, this R of 8 value is 700. And 81 minus 700 is clearly less than 0. So we've said that the IVT applies. We found a point where it's greater than 0, a point where it's less than 0. So there must be a point where it equals 0.